Alright, in this simulation I'm just going to show you the basics of a simulation that is on Falstad.com. This is a site that we used a little bit when we talked about waves. We're going to use it some more with electric fields and that type of a thing. These first two simulations have their uses. This first one is very similar to the FET one, only it's much more complicated, which gives you more that you're able to do, but it's a little bit less useful than when you're just starting out. This 3D one, however, I think allows you to visualize things that you otherwise would not be able to. So here it is, it pops up. You might have to allow it to pop up. Your computer might try to block it, that type of a thing. So I've got this up here, and right now it's showing us particles, what particles would do if you would just drop them into space at rest. And we can see that they're being attracted to this. And bear in mind that all of our particles are always positive test charges when we put them around a charge of interest. And so that indicates, hopefully you can understand that indicates that this is a negative charge. You can also look at some other features of this. We're going to focus on, well, I'll first show you the field vectors. So this is what the 3D field will look like. It's a little bit difficult to understand and to see what's happening. You can zoom in if you want to, or zoom out, I suppose. You can zoom in and try to get maybe a better understanding of what's going on by zooming in. But probably the more useful tool is to slice. So if I slice this up on one of the axes, you can see that I've got something that we're more familiar with. This looks kind of like the FET simulation. As I bring it off to the side, just by clicking and dragging, we can see that the field in this direction gets smaller and smaller. The reason being because as we get off to the side, the tendency for this charge to pull something here inwards becomes dramatically less. And by inwards, I don't mean not towards it. I don't mean towards it. I mean in towards the center of this slice. Okay, so we don't see much of that. They do show us, though, that they are angled in the direction of the charge itself. So I'm just going to get rid of that slice for now. And I'm going to switch from field vectors to field lines, which is one of the reasons why I wanted to show you this. So we've got the field lines in 3D now. And as before, the density of the field lines indicates the field strength, but Falstad also goes one step further and also indicates the strength of the field lines based on the coloration, or I should say the brightness. So we have pure white here, and it gets to a darker and darker green as it gets weaker. And you can still slice here. I have my X slice off to the side, and you can see that it's just a green, but as I move it towards the center again, it becomes much like our flat representation, and it has the white in the middle indicating a strong intensity. Moving off to the side, it gets less and less. Now you can also slice it in the Y direction and so on. For a single point charge, it's really not going to matter which way you slice it. However, we have a lot of options for what types of charges we might want to look at. For instance, here's a double point charge. This is two negative charges, and I can tell it's negative just by going and looking at what happens to the field vectors, right? And I can see that they're pointing inwards, so I can slice them if I want to in any particular direction that I like. And we can see the effect that has. As I move it off to the side, we should see that the field does still diminish. But one of the cool things about this actually is if I go to the field lines, as it gets off to the side, it actually doesn't look much different from when we had a single point charge. And I can actually make them a single point charge just by bringing them in and changing the separation to 0. And as I move them farther apart, it looks less and less like a single point charge. The reason being because if I have them like this, for instance, the space between them is not nearly as great as the distance to the points where we're measuring the electric field lines. And so the result is that these lines, these points in space, see these charges as almost a single charge. Now as I bring this back in between them, obviously they kind of hate each other, and so the field lines push off of each other, so to speak. And that leaves this gap in the middle where there's no force. There'd be no field right in here, a field of 0. We can also look at a dipole. So this is what a three-dimensional representation of the electric field lines of a dipole would be. Right? And we can just take a look at that, and you can see that the field strength gets smaller and smaller as we go off to the outsides. And as I bring them closer and closer together, you can see that the field strength outside gets less and less very dramatically. What I encourage you to do is just explore. So go through some of these, play around with different separations, get familiar with the way that electric field lines work, how they compare to electric field vectors, how it compares to particle velocities, and so on. We'll eventually get to displaying equipotentials. That'll be something that we'll talk about at some point in time in the near future, next section, so to speak. But for now, just focus on the things like the field vectors and the the electric field lines, because that's going to form a foundation for you to understand everything that happens after that. And one last thing that I would like to mention just briefly is that electric field lines are not just applicable to electric charges. We can use the same idea to deal with masses. Not obviously electric fields, but we could have gravitational fields. The idea of visualizing fields as lines, as vector fields, is a very important skill, and it's a very important tool that you need to develop so that you can easily represent and understand what's taking place in situations. So explore, and hopefully have some fun and learn some things while you're doing so.